So to get started here today, I'm mostly done with this lab section's first notebook, and I am working on getting through, I probably have a couple more left to finish up today that I'll finish after this. And then I'm going to finish up the next lab section that I teach, which is the other Tuesday class, the evening class. And the main thing that I wanted to inform everyone about with regards to our lab notebooks, let me go ahead and open up an example, and we can all find this within the files. If you look on Canvas, it's under, let me see what it's, lab notebook example. And the one that we have here, let me open it up so I can kind of make sure that nobody loses any extraneous points for this one. Everyone has been doing really well so far with regards to the main points of the lab notebooks that are critical and like hazard, answering questions. Y'all are doing great on that. Let me go ahead and share this lab notebook example so I can just have everyone review this with me. So right here, purpose, everyone did great. The main thing that I saw from the first lab notebook was that people are confusing the apparatus and instruments. So right here, list all of the apparatuses used. So the apparatus, when they say something like distillation rig, one example that people were saying for the first experiment was vacuum, it was vacuum filtration. So that is an actual, an active process. It isn't a specific thing. So whenever you say vacuum filtration, that is the act of performing that. But the tools that you would utilize would be a vacuum filtration, flask, beaker, a rubber stopper, and then your ceramic filtration funnel that you attach on top of it, and the rubber hose. So make sure within the apparatus section that you list out each one of those, materials. And then within the instrument section, that is specifically only the machines that we utilize. So for instance, for the recrystallization melting point, the melting point machine, the LabQuest, the stir plate and oven. For instance, for the instruments for the experiment that will be performed to the simple distillation, that will be something, like the heating mantle or a hot plate. And yeah, so just make sure that you understand the difference between the apparatus, which is the tools that we utilize, versus the instruments, which will be the machines that will be utilizing either to inspect something such as the melting point machine, or to utilize it to produce, heat as like a heating mantle or a hot plate. So yeah, just make sure that you mainly know the differences between these two, because I saw most people got these two mixed up, or they just listed the vacuum filtration as an apparatus, but that is an active performance that you do within a lab. It isn't a tool itself. You would want to list out every single portion of apparatus that is there. Everyone did well on the hazards. Make sure, if you list out the hazards, to go kind of in detail. If you're not going to do it in table format, you'll want to go ahead and make sure that you put what type of waste it is, the skin contact, eye contact, basically anything here. If something happened in lab theoretically and it happens, what do you do in that situation, or if it would affect you? The pre-lab calculations, any equations that we use throughout the lab manual, just go ahead and put them here, safe than sorry. We did pretty good here. I think it was only the percent recovery. Procedure, y'all did great on that. Make sure either you're utilizing a bullet point format or, step 1, step 2, 3, 4, 5, and then make it very legible. Try and do as close to full sentence structure as possible, so it's not like you just wrote a little note. You'll want this as if you were walking into a lab and you had to only perform the experiment with this lab manual, or sorry, this lab notebook that you have. So you would want somebody to be able to take your lab notebook, walk into a lab, and then replicate the exact procedure that you've performed. The data, y'all are given it, so make sure that you just put it in there correctly. Always double check your work before you turn it in. Post-lab calculations, y'all did awesome. And I wanted to address also that some students did get a very low percentage yield with regards to their data, and it was because the amount that you received, a pure sample that came out, was somewhere near below 10%. And this is possible within a reaction. You know, maybe something happened in the reaction, you just got a really low yield. And the recrystallization step, it's low yield just because that's your low amount of pure sample that you received from the reaction. So it is not something that is really having to do as much with the recrystallization unless you did it improperly, as it is more so the step before it. It is possible to lose some amount within recrystallization. However, if there is a substantial amount of pure product that is, you know, in the mixture of compound and you're losing it in recrystallization, then that means that you're maybe using the wrong solvent or something. But most of the time, it's a step before it that maybe you just didn't have too much of pure product you would have expected. And that's just a bold statement just to let you all know, because some people had data where it was 90% yield, and then some people had like 8% yield, and maybe looking at it, it's hard to understand the reasoning of why you would have such low yield. So that's just to clarify that. Post-lab calculations, y'all did good. Conclusion, y'all did really well. And then the post-lab questions, make sure, so when you do the post-lab questions, just for stylistic purposes, either write out the question and then put the answer, or answer the question in a full statement, as if, you know, you were answering, for instance, and I'm gonna go ahead and tackle this one here just to let y'all know as a small thing. It was question number 4 that y'all answered it, 90% of you answered it correctly with regards to if you were to put a hot solution into an ice bath and then it like too fast, you didn't let it just go to room temp and then put it in. It was correct that the recrystallization would mess up because you can have impurity fall out. But also, if you think about it, if you have a hot piece of glassware and it has hot solution in it, and then you dunk it into an ice water bath, what can happen is that the glass can shatter. It's kind of a rudimentary thing, and I'm counting points off of this just so that y'all understand it. But I mean, again, everyone's doing great so far with the grades that I've seen and the data within it. It's such a small ding that it's something that is a good life lesson as well, that you never want to take a piece of hot glass and then put it into a cold environment, because it'll shatter. Not only can it damage you, but it can also ruin the experiment. If you had like a full beaker of recrystallization, or a solution that was recrystallizing, and then you placed it into an ice water bath, it could not only shatter, possibly harming you, but also spilling all the solution out into the ice bath. And then you just have like a full ice bath full of your solution. And, you know, it happens in labs. And we want to learn that so that we can avoid it in case that were to occur in a lab that you were performing research in or something like that. So otherwise, everyone did really well so far on the first round of notebooks. And I'm going to go ahead and try and get through the second round this weekend as well. And let me switch my sharing over here. And I think I want to go ahead and get started with our discussion today of the modules. So let me go ahead and open up this here over to module. Okay, so simple distillation. We did fractional last week. Let me go ahead and share the screen here of the module so everyone knows that we're all on the same page. So right here, we're firstly going to read through, like we usually do, we're going to read through the manual together. Secondly, make sure that everyone watches video 1, video 2, and video 3 on your own time. Number 3, the pre-lab notebooks, we won't worry about this week because of the sheer quantity of people that are not going to be able to make the lab. So just make sure that everyone complete your notebooks, on time, and let me know personally. Email me if you have any issues with regards to, your power or your internet connection and everything, because I know everyone's, still recovering from the crazy weather last week. Fourthly, go ahead and, work on your lab quiz as soon as possible. And then, so here are the tools that we would be utilizing if we were to be performing simple distillation in the lab. I'm gonna go ahead and zoom in. So firstly, we have a round bottom flask here that we would be putting our solution into. Here is our graduated cylinder. And then here is a connection hose that we would be connecting over here to our apparatus that we would be running water through. And this would allow us to cool down our distillate in this condenser here. And actually, I like the picture here better because it shows the actual, let me move this over 1 second. Yeah, so this is the full setup. Okay, so your round bottom here is connected by a clip up to your adapter, and the thermometer here is placed right here, as you can see. The reason we have it here is so that way it is at the still head, and so when it's boiling up, it'll measure the temperature of the vapors that are here up at the still head. And then what happens is as it condenses up here, because it's cooler up here, then it'll actually come down the condenser, and then the water line, the hose would be connected right here, shooting water up into it. And then there would be another hose coming out of it, going out into your sink or something that would allow you to rid of the hot water. So what happens is the cool water actually comes up the bottom of the condenser and then comes out of here. And so what happens is the cool water is coming up and the heat is transferring into the cool water and coming out of the condenser down into the sink or your area to remove the water that you'll be pushing through the condenser. And all of these clips are here in order to make sure that everything's sealed. Make sure if you're in a lab to put a little grease around the ring. So you see here, there's all these like little rings, like the circular device that they go into each other. You'll want to put a little bit of grease around it so it creates a good seal, because the heat will expand the glass whenever you're utilizing it. And if you heat something and it doesn't have grease in between the glass rings where they hold into each other, then it can actually expand and it could possibly crack or just seal onto it and get stuck. And then once you're done with the experiment, you can't remove it very easily. So we always recommend to add grease onto these little sections. We utilize the clamps to hold them together. And then coming over here, we have this exit adapter, which will allow our distillate to come down out of at the very end. And this extra little portion here would also be utilized if we were using vacuum distillation, which is really awesome practice. However, we will not be utilizing that as much here. However, I will discuss it in the lab manual further so that everyone can get a little bit of clarification as to what the difference is. So finally, here we'll have our post-lab lab notebook, which will be like usual. Always feel free to ask me questions throughout the week before it's due, and I'll try and help you out with a little bit of clarification. I want to try and avoid giving you the answer outright, but I will try to steer you in the right direction, just so that way that you use this as a learning tool and not as much of a I just need to get that answer and get out of this class. Because we want to make sure that everyone learns as much as we can with these online classes, since we won't be getting that hands-on experience that we usually would be. So that's it for the module so far. Make sure to go ahead and go there like usual. Nextly, we will be going over into the actual lab manual, and I've gone through and getting a little better at this now to assist everyone by taking some notes that I can share with everyone. I think this will help everyone out a little bit more with their clarification. So here the introduction is a brief introduction just to giving an idea of extracting samples, recrystallization and melting points. But the primary thing here that we're going to be utilizing will be the two laws this week, Dalton's and Raoult's law. And I wrote here so everyone can see Dalton's law is the total pressure, which is equal to the sum of all partial pressures within a given system. So the summation of multiple different pressures of different compounds that would be within a specific boxed environment. If we would think of a theoretical square box full of 3 different gases, this pressure of each individual gas would add up to the sum of the total pressure of the system. Secondly, Raoult's law, the pressure of the solution is equal to the mole fraction of the solvent times the vapor pressure of the pure solvent. So here, the vapor pressure of the solution, which is equal to the mole fraction of solvent times the vapor pressure of pure solvent. And we'll go further into detail with that as we go further down. We'll go down into more of a derivation of the equations. So going forward, the concept of boiling point in itself, we are looking at a closed evacuated system as that theoretical box that I was speaking about. And we'll want to look at the idea of equilibrium vapor pressure. So the magnitude of vapor pressure at a given temperature is called the equilibrium vapor pressure of the liquid at that temperature. So with relation, if you think about in Chem Chem, PV is equal to nRT. The pressure is related directly to the temperature. So at a different given pressure, there will be a different given temperature that a liquid will boil at. And so as you see here, vapor pressure is temperature dependent, shown in figure 4.1. And we'll go through this here once I get through this part here. So we want to remember here that as the temperature of a system rises, the average kinetic energy of the liquid molecule increases. So you can also think about it as in terms of physics as well, that the kinetic energy is increasing as the temperature increases in the system. And that is actually allowing the escape of the liquid into the gas phase. So when we look over here and look at this graph of dependence of vapor pressure on temperature for a liquid, so what they're saying is if you reduce the pressure down to theoretically 100, the temperature of this given liquid could boil here at 0 degrees Celsius. And so when you think about the idea of what does it mean to have a pressure reduced system, because 760 torr or 1 atm is at the pressure at sea level. So that's our standard that we utilize. And if you want to think about, well, what is, this 100 torr, how do you reduce pressure? You would put it under something like a vacuum line, such as like vacuum filtration is how we pull things down. That vacuum is creating a reduced pressure within the system. And you can utilize that within a sort of distillation. So on that part where there was that little inlet, we can attach a hose to that and then run a vacuum onto it. And it would actually reduce the total pressure of the system. So you would have to put in less kinetic energy, less heat, whichever way that you want to think of it. You would have to utilize less heat in order for that solution to boil. So here, as you can see, that the normal standard here for this given substance is at a boiling temperature of 60 degrees Celsius at 1 atmosphere, 760 torr is right here. However, if we were to reduce it, let's say to 500 torr by a vacuum, then we could actually only have to raise the temperature of the boiling substance to 45 degrees Celsius in order for it to boil off. And this is just a relation with regard to vapor pressure and temperature. So just remember that golden rule of PV is equal to nRT, pressure times volume is equal to moles times Raoult's constant times temperature. So, and we'll make sure here that there's a very important safety rule, and this is just a good thing for everyone to learn here, that you would not want to increase pressure in a closed system because the temperature can increase and it can cause an explosion, because if you're in a closed system, then there's nowhere for all of the expanding molecules to go, and eventually it becomes so much under pressure that it just explodes. Kind of like when you press onto a balloon, and when you start pressing the pressure onto the balloon, well, now you've compressed it and the total amount of molecules in there haven't changed. So what happens is all of a sudden you get to a certain equilibrium point, and then it explodes because it can no longer, take up the space within that given system. So as they say here, never heat a closed system. So if we were performing vacuum distillation, there is always an exit of the pressure, which is going outside of your vacuum device. So that it's not technically a closed system, it's a reduced pressure system. And there's an exit going out of the pump that is pulling, or in the case of like on a sink that you probably utilized in Gen Chem, where you've turned the water on to pull to pull the pressure from a system, like in vacuum filtration, that the water is acting as the exit of the system. So it's not closed, it's actually pulling from that water. So going forward, we'll go ahead and look here. The total pressure above the liquid is defined by Dalton's law of partial pressures, which is here, equation 4.1. It is equal to the sum of the given partial pressures of sample and of air. The partial pressure of the sample is equal to its equilibrium vapor pressure at the given temperature. So here, the total pressure of the system is equal to the pressure of the sample plus the pressure of the air. And this is a better example of more of the system that we're using here, because we'll be performing this within open air. And so what happens is that we'll have a net effect of displacing air whenever we are, increasing the temperature of a given system. So at the higher temperature, the partial pressure of the sample will be a larger percentage of the total pressure, because what happens is that the air is being displaced, whereas the pressure of the sample is increasing as we increase this temperature. So going forward, when the temperature of liquid is such that the equilibrium vapor pressure of the sample equals the total pressure, the rate of evaporation increases dramatically and bubbles form in the liquid. So this is explaining whenever we meet that dotted line on the liquid to gas line there with the vapor pressure. And so what happens is that boiling occurs, and we associate this with the statement of the boiling point, which everyone already knows of what the boiling point is. It's just explaining here the relation between the vapor pressure and coming to that point of boiling, called the boiling point. So more to explain as to why we're egging on this concept, it is coming down here to, and I really wanted to make sure to highlight this for everyone to see. So for example, for this molecule here, boiling point of 132 degrees Celsius at 748 torr. So you see, this is at a little bit lower than atmospheric pressure, such that the boiling point, if we were to measure it at 760 torr, it'd be maybe 133, right? It'd just be a little bit higher. It's all relative to that equation that we utilize up there. So the boiling point of water is 100 degrees Celsius only when the external pressure is 760 torr or 1 atmosphere. So, if we were to lower the pressure of the system, then water would be able to boil, let's say 90 degrees Celsius, 80 degrees, it depends on the relative pressure that is within this given system. So moving forward, suppose that a liquid has a normal boiling point such that it decomposes appreciably when it's heated to a given temperature. Reduction in the total pressure of the system reduces the boiling point of the sample to a temperature at which it no longer decomposes. So this is really good. Let's just say that you have a liquid that decomposes at 80 degrees Celsius and you don't want it to decompose, but you want to distill it off, right? Well, you can reduce your pressure down in vacuum distillation, where you attach a hose to the side of your distillation apparatus and reduce your pressure down. And then let's just say it reduces down from 80 degrees all the way down to 40 degrees Celsius. You can safely distill it off without decomposing the chemical at hand. It's kind of like if you burn food on the stove, once it's burnt, it's burnt. The same thing can happen with a liquid that can decompose. It can just decompose off and create separate substances that you're not wanting to have, such as something like maybe ethyl acetate. You can look that up after this class, composed of an acetate ion and then an ethyl group. But if you were to decompose it, you would get ethanol and then acetic acid. So something like that, you wouldn't want to destroy the liquid that you're trying to distill. So this is where vacuum distillation would be a great technique. And also you don't have to add as much temperature into the system. So not only does it create a harm reduction system for you, where you have less temperature needed to put into the system, but also you can just reduce that pressure, and then you will perform it faster, easier, and it's a very good thing to utilize in lab for things that have very high boiling points or can decompose at very low temperatures. You can just reduce the pressure of the system and then boil it at a lower temperature. And it was super useful. I really hope that people get to utilize that at some point within their science careers, because I personally love utilizing that. So going forward, simple distillation now allows separation of distillates from less volatile substances that remain as pot residue as a completion of distillation, such that when they say less volatile substances, they're talking about the relative boiling point. So let's say you have a chemical that has 120 degrees Celsius, something close like toluene, and then you have something like ethyl acetate, something near like 80 degrees Celsius. You can perform simple distillation and easily pull your ethyl acetate out of it because it is less volatile, and then you'd be left with your toluene at the bottom, which would be more volatile. Or sorry, I have it backwards there. The less volatile would be toluene because it has a higher boiling point, and the more volatile would be ethyl acetate because it has a lower boiling point. So the lower the boiling point, the more volatile it is. You could just think of something, its ability to evaporate, like isopropyl alcohol is a good real life example. If you poured a little isopropyl alcohol on your counter, like rubbing alcohol, it would evaporate a lot faster than if you spilled a glass of water on the counter. So that's a good example of a real life system where you can see the difference that water is less volatile than rubbing alcohol or isopropyl alcohol, which is more volatile because it has a lower boiling point than the other one. So in this system, we'll be utilizing a single component separation in a simple distillation system, which is different than the fractional distillation that we covered from last week. And it allows the isolation of various components of the mixture and acceptable purity if the difference between the boiling points of each pure substance is greater than 40 to 50 degrees Celsius. If not, then we would be utilizing more in-depth technique like fractional distillation. So here, diethyl ether, a boiling point of 35 degrees Celsius at regular atmospheric pressure, and toluene. So see here, they utilize a good separation here because 35 degrees Celsius versus 111 degrees Celsius, you'll get a really, really obvious separation whenever you perform simple distillation, so long as you utilize very slow heating and just very, very cautious, attentive boiling of this. Because if you heat it too fast, you'll get a mixture and perform sort of a fractional distillation, whereas we're trying here to just perform a simple distillation. You rise it very slowly in temperature up to your near 35 degrees Celsius boiling point of diethyl ether, and then you would boil off the diethyl ether, it would come up to that still head, and then slowly cool down with your condenser, and then distill off over into your collection flask. So going forward, this goes into a more in-depth explanation if you want to read forward at your convenience. So now we want to look here at a good example to describe the differences of having a compound mixture versus a pure sample, or pure liquid in this case. So curve 1 corresponds to the dependence of the temperature upon vapor pressure of pure water and intersects in the 760 torr line at 100 degrees Celsius. So curve 1 right here, normal water, as you know, boiling at 100 degrees Celsius, over here at the regular 1 atmosphere 760 torr. However, curve 2 here is a solution having a particular concentration of sugar and water. So you can notice that the presence of the non-volatile impurity, sugar, reduces the vapor pressure at any temperature by a constant amount. So anywhere along this line, you can have, if you lowered the vapor pressure and you want to boil it, it would boil off easier. And as you can see here, that going all the way over 760, then it would actually, with this sugar line, as they're saying here, the temperature which this curve intersects the 760 torr line is higher because of the lower vapor pressure. And consequently, the temperature of the boiling solution, 105 degrees Celsius, is higher. So I think I may have said that backwards, so I'm going to go ahead and re-clarify what my statement was. If you put sugar into water, it'll increase the boiling point. So here, we would have to run it at 105 degrees Celsius in order to boil it at 760 torr. And this is just showing that in this system, it's making it harder to boil off water because you have that sugar mixture in there. So despite the presence of sugar in the solution, the head temperature in the distillation will be the same as for pure water. So when you're boiling down in the little round bottom flask and you're boiling your water and sugar solution, when water boils up and it meets up at the head of the distillation device, up there where you saw the thermometer was, then that will be 100 degrees Celsius regardless, because that is the boiling point of pure water. The boiling point of water mixed with sugar, as they're saying here, is 105 degrees Celsius. But at the very top, where you're getting your pure water distilling off, the head temperature will be 100 degrees Celsius, and then it'll distill down, through the condenser. So as water distills, the pot temperature will progressively rise because the concentration of sugar in the distill pot increases, further lowering the vapor pressure of the water. So the pot temperature, you'll have to keep increasing it because as you boil off the water, then you have a higher ratio of the sugar to water. So at the start, you have some ratio of sugar, some ratio of water, and then you're slowly lowering the amount of water, so you're increasing the overall concentration, the mole fraction of sugar to water. And so what happens is, since we already know the sugar is increasing the boiling point of the solution, then it'll further increase the boiling point more and more and require more energy to pull off more of the pure water. So nevertheless, the head temperature still remains constant because pure water is being distilled off. So that gaseous phase of pure water meeting up at the still head is still going to be 100 degrees Celsius. The quantitative relationship between vapor pressure and composition of homogeneous liquid is known as Raoult's law down here, which here again is the pressure of the total solution, which is equal to the vapor pressure, Px. I should highlight that here real quick for everyone. And remember, it's the Px represents the partial pressure of component X, and it's equal to the vapor pressure P naught X of pure X, in this instance, we would say water in that water sugar example, at a given temperature times the mole fraction, and NX is always the mole fraction of X, which is the water in this example, in the mixture. The mole fraction of X is defined as the fraction of all molecules present in the liquid mixture that are molecules of X. So it's the mole fraction of X, the full solution relative to that pure water that is within this sugar water mixture they're talking about. So it is obtained by dividing the number of moles of X in a mixture by the sum of the number of moles of all components. So the mole fraction is as the relative amount of subject X within the total amount of components of the entire system. And Raoult's law is strictly applicable only to ideal solutions, and we just approximate that everything that we perform in lab is this ideal solution for calculation's sake. There are more advanced derivatives going forward into physical chemistry if you have to take that class, but we'll only keep it very simple here and make it that fortunately many organic solutions approximate the behavior of ideal solutions. So just keep that in mind, that we'll be utilizing equations 4.1, Dalton's 4.2, which is Raoult's law, and then equation 4.3, which is the mole fraction equation in order to solve for your mole fraction. So going forward, notice the partial vapor pressure of X above an ideal solution depends only on its mole fraction solution and is independent of the vapor pressures of the other volatile. So it's only relative to its relative pressure, its relative boiling point, and the others are independent. So each separate component of the system, such as ether and toluene, the ether's boiling point is only relative to ether's boiling point and is separate from toluene, whereas the boiling point of water is only relative to its boiling point and not towards the sugars. The total solution itself requires more energy to remove that pure water, but even with that concept, we still have to remember at the end of the day that the pure water at the still head is still 100 degrees Celsius because it's a pure ideal solution of water when it's boiling up there. If all components other than X are non-volatile, the total vapor pressure of the mixture will be equal to the partial pressure of X, since the vapor pressure of the non-volatile components may be taken as 0. So this is like an ideal equation where you cancel something out within an equation. The non-volatile compounds may be taken as 0 because their pressure is irrelevant towards the equation that we'll be utilizing. Thus, the distillate from a mixture will always be pure X, such that sugar as a non-volatile substance will not boil off in the system. That's why we have this pure sample of water coming off at 100 degrees Celsius up at the still head. So coming forward here, when a mixture contains two or more volatile components, the total vapor pressure is equal to the sum of all partial vapor pressures of each component. And this is here where you add in, the example I gave at the beginning. Let's say you have 3 components, X, Y, and Z. This is known as Dalton's law, where Px, Py, and Pz refer to the vapor pressures of the volatile components. If you have 3 volatile components in a system, you'll have the pressure of X, the pressure of Y, and the pressure of Z. So then you can break it down, and together you will get a total pressure of the full system that is, found by Dalton's law. And so finally, this part here going forward is the full procedure. Make sure to write it out in your own words in your lab manual. Here is an example of the system that would be the simple distillation device. So here we would want to utilize an electric heater or a heating mantle and not a Bunsen burner, because we'll be utilizing volatile substances such as cyclohexane, and that is a flammable substance. So if it were to ignite, it could either catch on fire or explode the system. And so we'll utilize electric heating mantles, substances that are allowing us to heat, or maybe a heating plate with an oil bath, such that we don't utilize an open flame and possibly ignite the solution we're trying to distill. So here's a support ring to hold the heating mantle. Then here's the electric flask to heat it up. The round bottom flask here to hold our solution. You put the boiling chips in there to allow it to boil. And then there's a clip here holding the round bottom flask. Then you have the adapter here, the distilling adapter, and the distilling head, which is this area where the pure substance such as water comes up, and you would measure. You see the thermometer? It's not down in the solution. It's actually up here at the distilling head in order to measure the distillation, the distillate that comes off. So the 100 degrees Celsius would be seen there when pure water starts to vaporize up there and would condense here. As you can see, water comes in the bottom of the condenser, flows up, and then comes out, because the cool water comes in from the bottom and goes up. And then as the hot water that is distilling up and going down the condenser wants to cool down. So it's basically passing each other and allowing that water to condense and cool down back into liquid phase and then come down here, just clamps to hold on to the system. And then an adapter finally to allow the condensed liquid to drip down into the receiving flask or graduated cylinder in this case. And then we always utilize support stands for us to be able to set up systems to set up our apparatuses to perform the experiment. So going forward, this is further of the lab manual. Make sure to write all this out. And then, of course, answer out post-lab questions. Everyone did really well so far on the post-lab questions and the lab notebooks. I'm really happy everyone's getting it. Just make sure to take a look at the notes that I'm leaving on the side of your grade, so that way going forward that you don't make the same mistakes. And if you have any further questions for that, always feel free to email me. Let me go ahead and switch this back over here. And let me see. So here, Dr. Rastogi had given us an example, and you can find this also in Canvas for simple distillation or Stogie PDF. And he gave here an example of the drawing as we went here and reviewed. Make sure to get your hazards and safety written down correctly so that you get your full points. The idea of this cyclohexane and here in a non-volatile dye, put inside of the round bottom flask with some boiling stones, and the immersion line to never go below the distillation head. So this is a good thing to review for you to be able to see once again the idea, but I believe that after you watch the other videos as well that are given in the module, you'll kind of get the rhythm of what's going on with the simple distillation, especially if everyone's already reviewed everything from fractional distillation. And so finally, the data. Let me go ahead and save this one moment. Your screen here. Students should use the following data table to calculate the percentage recovery of cyclohexane for completing the procedure. Use the data table based on your first name and the alphabet. Students should complete all the post-lab questions as well. Make sure to attach that in at the end of your lab notebooks as usual. So if your first name starts with A through C, utilize this. C through F here, G through K here, L through N, O through Q, R through T, U through W, and X through Z. And make sure to calculate your percent recovery as usual. Very simple formula. And that looks like it's about it for today. Let me go ahead and open the floor. Does anyone here have any questions before we go ahead and close up our meeting for today?
Yes, just to be sure, both lab 3 and 4 are due on Sunday.
Yeah, let me go ahead and open up the email so we can go ahead and review that as well in case anybody else is thinking of that watching this video after hours. So let's see. Okay, module should be under, I believe there's a section I can check for the calendar for everybody. Let's take a look here. Okay, so here, quizzes, let's go down. The fractional distillation quiz has been extended up to the 26th, which is Friday. And the simple distillation quiz as well is due this Friday. So if anyone hasn't completed the quiz yet on fractional distillation, it is due this Friday at 5. As well, the simple distillation one will be due at 5. And then let me find the lab notebooks real quick. Should be able to find the calendar for this. Okay, here we go. Screen. Okay, so on my calendar here, it shows that the notebooks, I'm not sure exactly why they've been extended out for the first two. However, the 4th and 5th notebooks, yes, they are both due on the 28th of February. If there's any other issues that we're having with regards to power or internet difficulties, please let me know directly, and we can work together to get it extended out a little bit. But primarily, if you can get access to it on PDF on your phone, you should be able to write it down on a notebook and get started with it. But, you know, of course, I totally understand with the weather concerns and everything from last week, everyone's having a lot of power difficulties and internet access issues. So if there is any disruptions and, you know, we need to extend it and at any point, please let me know. Otherwise, I'd say definitely try to utilize internet on your phone to download the PDFs so that way that you can you know, take the lab manual information and then put it onto paper or put it into a Word document and then get it uploaded at the earliest convenience that you can.
Hey, Scott, I came in late and I guess I missed some stuff. So this lab we're doing is, we're doing the we're talking about the simple distillation lab today, right?
Yes.
And we're also having the fractional distillation lab.
Right. So refer back to the email that I had sent out in Canvas, and the fractional distillation video have been posted from last week. So just at the earliest convenience that you have, go ahead and review the video I posted on YouTube for the fractional distillation. And then the quizzes for the fractional and simple will be due this Friday by 5 p.m. and both lab notebooks will be due by Sunday. But if you have any sort of disruption, still, please let me know in a separate email, and we'll work together to get it turned in, you know, at the earliest convenience.
Okay, I got to find that email. Because yeah, we sent that in video form, like essentially what you went over the lab manual lecture type of thing in video form. So, okay.
Yeah. So just go ahead and check on Canvas, and there should be some inbox messages that maybe it didn't get sent. You might not have notifications set on because I didn't have it for a while and it wasn't sending to my email. But if you log into Canvas, there should be under our organic chemistry section, there should be a few inbox messages from me and Dr. Stogie and and some announcements as well. I'm going to send out another link to the YouTube channel for everyone in the Canvas, so that way that everyone can go ahead and click the link as well. You can review this video that I just finished up with reviewing our lab manual for simple distillation on YouTube afterwards. And all of the material that we covered today will be reviewed on there. Okay, so if anyone else has any questions, please feel free to ask now. Otherwise, you are free to go.